Welcome everyone to Cloud Data Management Day. I'm so excited that I get to talk to you here today about data warehouse, data lake, data mesh, oh my. We're going to talk about the history of data storage, starting all the way back from our lonely elementary scenario database. And we'll dig in deep on what is each of these pieces, what problems did they solve, what benefits do we have, and in particular, data mesh. Is it worth it? Let's take a look. Here's the part where I tell you I am definitely going to post the slides on my site tonight. A lot of speakers have said that, and I ended up chasing a speaker for a good long time trying to get their slides, which is why you can go to robrich.org right now. Here's robrich.org. Let's head there. We'll click on presentations here at the top, and here's data warehouse, data lake, data mesh, oh my, the history of data storage, and the slides are online right now. Achievement unlocked. While we're here on robrich.org, let's click on About Me and learn about some of the things that I've done recently. I'm a friend of Redgate, a Docker captain. I do a bunch of things with Microsoft technologies, and I'm also a Jetpack IO developer advocate. If you're struggling with Kubernetes, I would love to learn with you. Some of the other things that I've done, SQL source control basics, mine is chapter 8. That was a lot of fun, doing source control with databases. And one of the things that I really enjoy is AZ Give Camp. AZ Give Camp brings volunteer developers together with charities to build free software. We start building software Friday after work. Sunday afternoon, we deliver completed software to charities. Sleep is optional, caffeine provided. If you're in Phoenix, come join us for the next AZ Give Camp. Or if you'd like a Give Camp where you're connecting from, hit me up on email or Twitter, or hit me up here at the event, and let's get a Give Camp in your neighborhood too. One of the things I'm particularly proud of, I replied to a .NET Rocks podcast episode. They read my comment on the air and they sent me a mug. Woohoo! So there's my claim to fame, my coveted .NET Rocks mug. So let's dig into data warehouse, data lake, data mesh, oh my. We talked about this guy. So data mesh. Have you heard that term? Is that like one of the new buzzwords floating around? Is this a fad? Should I just skip this one and hit the next one? After all, I'm still amortizing the cost of my data warehouse. Let's see. Let's dig in. Now we're going to talk about database, data warehouse, data lake, data mesh. We're going to see how each one solved a very specific problem and how, based on solving that problem, we might have created new problems that we didn't foresee yet. We'll get to see how each one upgrades our approach to data, and really how we can facilitate data throughout our organization. Finally, we'll dig in deep into data mesh, and we'll take a look at what is data mesh, why is it better, or should I just skip this one and move to the next one? First up, databases. Back in the day, we had properties, and we needed to store data. So let's store some data. We probably have a monolithic application, so let's build a monolithic database. We can draw a boundary around this application with a VPN. So, there isn't a big need for data security. We just have a user using a machine. They have some forms over data app, and it stores data in the database. Yeah, this is pretty easy, pretty clean. The database doesn't evolve all that much. The application doesn't change that much once we've got it in place. And so this works. A little bit later, we say, well, let's make that database a little bit more standard. Let's build this structured query language, or SQL. Now, what's really cool was SQL was created in the early 1970s. Thank you to Donald Chamberlain and Raymond Boyce from IBM for building what we now know as SQL. SQL brought us some really elegant constructs. We have rows that store data. We have columns that are consistent across our data store. So if I have a column that is, for example, a phone number, everything in that column will be a phone number. Now we can normalize data. Now the process of data normalization was to make data fit in this really sparse data intense spot. Now we didn't have a whole lot of storage space. Space was measured in megabytes back here. And so we really needed to use that space as optimized as possible. So we created data normalization. It avoided data duplication. Now that's great. We can store data smaller, we can create joins between tables, and that allows us to store this data in a very, very compact way. We also have ACID compliance with SQL data stores. Let's double click in ACID compliance. With ACID compliance, we know that either the entire set is going to succeed or it's going to fail. We're not going to get some of the data in, but not others. We're not going to get part of the data set committed, but not the rest. Either it all succeeds or it all fails. By comparison, we have eventual consistency. If I go up to a shopping site and I put in my order, they're not going to keep that page just spinning until the package shows up at my door. Similarly, if I book a flight with an airline site, I'll probably get an email saying, I'll probably get to a page that says, thanks for booking your flight, but I won't have my confirmation number. I may not have a ticket ID yet. And then I'll get an email later saying, here's your net result. If I walk up to Starbucks and I make a purchase, and then I immediately go check my account balance, that purchase probably hasn't been withdrawn from my account yet. Now, when I get my monthly bill, of course, I'll see that charge and everything will be fine. Eventually, these systems are consistent. But if I do an update and then I run around really fast and I get my status, I may not show that update. Eventual consistency is that compromise of, well, we'll reconcile it later. So we have ACID compliance here with SQL databases. We also have database normalization. It allows us to store data in a very compact and efficient way. Now, these database characteristics really mirror the monolithic application that we're using. We can really easily search for a row, then add or update it. We have this slowly evolving schema. And so the on-prem network is that security boundary, and we really don't have to worry about it beyond that. Now, that was great for our applications in the 70s and 80s, maybe even into the 90s. We've got security is easy, changes are rare, strong schema, small storage. It's looking pretty good. And then a few years later, our needs changed. Hey, let's report on this data. I want to aggregate all of these transactions and I want to be able to report on them in interesting ways. So we build a system kind of like this. Now, we still have our transactional system that is hitting our database, but we also have an analytical system that is hitting our database as well. Now, maybe these users are the same, maybe they're different, but this one's doing adds and updates. And this one is just querying data, but it's doing it in bulk. So we have very different usage characteristics between the transactional content and the analytical content. And that puts different characteristics, different needs on the database. We need to do bulk reads, and we don't write. That's very different from our transactional system that is about searching for data and then updating it. We don't do bulk reads when we're doing transactional things. We just do quick searches. Analytics. So we're querying differently than we were with the transactional system. These queries are slow because, well, we're reading a lot of data, and we're probably locking the table as we do these queries. Now, as anyone knows, if we're locking the table, then of course the system is going to suffer. The transactional system is waiting for those locks to unlock so that it can get the rest of the content. And now we have this really contentious relationship between our transactional needs and our analytical needs of this data store. Now, maybe we could do things like read uncommitted. Now we end up breaking the ACID compliance boundary. And so now we might have some content that is part of the new transaction, some content that's part of the old transaction. We're not even in a consistent state. So yeah, analytics works very differently from transactional. Where our system before was really simple, now that we've added analytics, we have a whole lot of interesting cons here. In particular, those locks put on by the analytical database based on these slow queries is really hurting the performance of our transactional system. Well, what can we do? Well, analytics, because it locks the table, we're breaking our transactional needs. So how do we make analytics fast? Let's see if we can upgrade this methodology. Let's take a look at online analytical processing, or OLAP. Compare that to online transactional processing, OLTP. So with OLAP databases, let's separate the transactional system from the analytical system. Now the analytical system can focus on bulk reads and optimize for that use case, and the transactional system can focus on searches and singular row updates. Great. So this transactional system will do seek for rows and then read and write a few rows. An analytical system will do those bulk reads and no writes. And we end up with a diagram like this. Now we still need to get our data from our transactional system into our analytical system, but our user is using their data entry app on the transactional system. That works great. And our business user is using the analytical tools to get at the analytical data store. It can now do bulk reads. And is it choosing to lock? It doesn't matter. We're not locking out anything else. And then we have this ETL process, this extract, transform, and load. Periodically, it's going to load data from this database. It's going to transform it in a way that makes sense. And it's going to load it into this new data store. So it'll extract it from here, transform it, and load it here. Now that's a bulk read, but it's only happening once in a while. It's not happening all the time. So hopefully we're hurting our performance less. Not to say that we're not hurting performance at all, but hopefully we're hurting it less. Simultaneously, the nature of our OLAP database is that, well, we don't write. And now we're writing sometimes. Hopefully we're doing it in batches and we're modifying it to fit. We might even go from ETL to ELT, which is kind of fun. Let's export the data, load it here, and transform it in place. That can be kind of fun. So now we have OLAP databases. And now we have that massive need. How do we get data from here to there? How do we get it out of our transactional system into our analytical system? And thus the extract, transform, load process. The process of getting data from the transactional system to the analytical system. We call it ETL for short, extract, transform, load. Now this extract, transform, load is the process of moving that data from our transactional system to our analytical system, and we'll do this periodically, maybe nightly. We'll select all the recent transactional data, and we'll write it to our analytical store. It is a bulk read on our transactional system, which probably yields the locks that we have, but it's much less frequent than doing all the analytical queries on our data store. Maybe we can do it off hours to avoid the impact to our transactional system. And thus, we're brought to our ETL dilemma. If we do this ETL process more frequently, then we'll have fresher data for our analytical system. If we do this process less frequently, we'll have less impact on our transactional system. So, should we turn up the frequency really high to make our analytics near real time, potentially impacting our transactional system? Or should we turn down the frequency of our ETL to ensure that our transactional system is performant, but yielding maybe stale reports out of our analytical system? That's quite the dilemma. So when we take a look at OLAP databases, our goal was to separate transactional and analytical processing so that we didn't end up with these analytical locks on transactional systems. How'd we do? Well, because we have this separation between the two, our analytical systems can grow differently. Our queries no longer collide, and that's really great. This ETL process is a lot lighter weight than extracting the data every time we need to run an analytical query. We're still extracting data from our transactional system, but because we're doing it less frequently, hopefully that impact is a lot less. But we're left with this dilemma. If we do it more frequently, we impact the transactional system more. If we do it less frequently, our analytical reports are stale. So On the upside, it requires ETL. It requires moving data from our transactional system to our analytical system. And we end up with this compromise. Should we turn up the frequency and have more real-time reports, or should we turn down the frequency of ETL and have less impact on our transactional system? Okay, so OLAP is doing pretty good. A few years later, let's see if we can upgrade OLAP databases. Let's tune the analytical database for queries. And thus, we bring the data warehouse. Now, what's really cool about a data warehouse is we can modify our schema in our analytical system to grow it towards the queries that we need to produce. We can facilitate faster and easier reads. Now, we're less constrained by data storage now. We've grown out of the megabyte storage, perhaps into the gigabyte or terabyte storage era, and so it doesn't cost us quite as much to keep data around. We end up with a graph that looks not all that different from OLAP, but we've very specifically identified this as a data warehouse whose schema may or may not relate to our transactional system. This data warehouse has a schema optimized for the type of queries that we need to read. Perhaps we've denormalized it. Perhaps we've modified data. Yes, we end up with data redundancy, but the whole point of data normalization was to facilitate small storage and not needing to update so many places. We're not really doing updates here, so yeah, we have duplicate data. It makes the reads faster though, and that's really what we're after here in the data warehouse. So what are the optimizations we might choose to make as we move from an OLAP database into a data warehouse? Well, first off, let's remove foreign keys. The whole point of foreign keys is to validate the data exists in that other table when we're doing an update. In an OLAP database or in a data warehouse, we don't really do updates outside the ETL process. So let's remove the foreign key validation. That'll save us all of that time when we need to validate it. And yeah, we may find that this relation doesn't match when we're querying data, but this is not a write system. It's a read-only system. So yeah, our source data is in error here. When we remove the foreign keys, our system runs faster. Excellent. Next, let's create different indexes. Now we can create indexes optimized for our analytical needs, not for our transactional needs. Maybe in our transactional system, we had indexes on each of the primary keys, maybe each of the foreign keys. Here in our analytical system, maybe we choose not to index based on primary and foreign keys, but maybe we'll index based on dates or regions, those things that we want to bulk query against. Let's optimize this data store for these analytical use cases. Now, the transactional system can definitely be optimized for the transactional needs, but any compromises that we made in the schema of our transactional system to try and make those analytical queries a little faster is also no longer necessary. So our transactional system can really optimize for the transactional use case instead. That's really cool. Let's tune our indexes for the purpose of our system here. So transactional system indexes can focus on transactional needs, and analytical systems can focus on our analytical needs. Next, let's denormalize the data. Now, why did we choose to normalize the data? We chose to normalize it because data storage was small. And now that we're less concerned with small data storage, then we can avoid the cost of rehydrating all of the joins by denormalizing our data. It was important when we had storage in the size of megabytes to optimize for the smallest storage space. Now that we can measure our data store in gigabytes, terabytes, petabytes, and more, then storage space is no longer the concern. So optimizing for it is no longer necessary. Our other reason for database normalization was to avoid needing to update multiple places if data changed. Here in our data warehouse, data doesn't change. So we don't need to optimize for avoiding redundant writes. We don't write here. We only do bulk queries. So let's denormalize our data. Maybe put the customer name inside the order table. Now we don't need to join on the customer table to be able to get at order analytical queries. Yeah, we're removing duplicate. We chose database normalization to remove duplicate data, more compact storage, to fit in a limited disk space, and to optimize for minimal writes. These are not concerns now that we're in our analytical space. So we're specifically not optimizing for minimal storage space. We're optimizing for read performance. Here's an example of normalized on the left and denormalized on the right. On the left, we normalized our data. We have a customer table and an order table. Inside of our order table, we have a customer ID that relates back to the customer table. That means that we don't need to store John Doe and Jane Doe in multiple places. In our denormalized data structure, yes, we are storing the customer name in both places. Maybe we still have the customers table if we want additional details, like maybe their credit balance or their last purchase date. But here in the order table, if we want to be able to group based on order name, or we want to group by other details inside the customer table, we can denormalize that data so we only need to read one table. Let's only read the orders table. Now, because we're only reading one table, that read is faster. We don't need to do that computation of a join to do the analytics. And yeah, we've optimized for our read query. It does mean that we have redundant data, but we're not optimizing for storage space. We're not optimizing for avoiding duplicate writes. We're specifically optimizing for performant reads. When we denormalize our data, we're able to meet those performant read needs. So our data warehouse, what else can we do outside of removing primary keys, indexing differently, and denormalizing? Well, here in our data warehouse, we can start to experiment with different storage mechanisms. We could do NoSQL or a column store. Now that's really cool. Let's take a look at row store versus column store. Here on the left is a traditional transactional database, a row store, and on the right is a column store. Now, in a column store, we don't write the data to disk based on each row, rather we write it based on column. Now, what if I have, for example, states in the United States or countries in the world? There's only a limited number of countries, so I can probably compress this data really easily. So now if I want to do analytics on countries within the world, I can quickly bulk read all of the entries associated with that country. That makes it really elegant. Now, certain data compresses really nicely in a column store like this, and certain data doesn't. For example, address or phone number. Phone numbers are going to be different for each person. So if I'm doing a column store based on a phone number, I'm probably not gaining a whole lot. We could think maybe a column store is kind of like the index in a transactional system. We're specifically optimizing for bulk reads of that data. Some of the other things that we experiment with outside of column store is NoSQL. Now, NoSQL is really interesting. NoSQL takes a very different approach to SQL. SQL focuses on this really English-based query language and normalized data. By comparison with NoSQL, we basically have a JSON document. Now, different NoSQL data stores may choose to store it in different forms. Maybe it's a binary interpretation of a JSON document, but JSON's kind of a good methodology for thinking about this. What's interesting here is a JSON document doesn't necessarily have to be flat. In this case, we have a list of favorites, and we've embedded another table inside this table. Well, not really. We've embedded other details inside this JSON document. So that means we don't need a foreign key lookup. Excellent. We can also create here in these NoSQL data stores different rows for different types of data. One document in a collection doesn't need to be the same schema as another document in another collection. That's excellent. Now we can store whatever data is here. Now, as we start to experiment with these data stores, we might get to a point where we're avoiding redundant reads. We don't need to do foreign key lookups. And we've compressed the data into a really elegant mechanism where we can start to query it really simply. Next up, we can start to play with horizontal scaling. Now, horizontal scaling is really cool. We have more read-only nodes. Why didn't we horizontally scale our transactional system? Well, our transactional system was based on, uh, was built when we didn't really have multiple processors. And it focused on keeping consistency. Let's take a look at the CAP theorem. Here in the CAP theorem, we have consistency, availability, and partition tolerance. And so says the CAP theorem, you can have at most two. Let's look at it visually. So we have consistency, availability, and partition tolerance. We can either choose two or we can choose one really hard. Well, if we're starting to distribute horizontally, we focus on partition tolerance. We're going to say if the partitions start to diverge, that's going to be okay. We're focused more on availability and partition tolerance and less on consistency. Well, in an ACID compliant system, we're focused really hard on consistency. So we're moving more away from ACID compliance towards partition tolerance. Now, in a read-only system, such as a data warehouse, maybe that's less important. Consistency is unimportant because we're just bulk updating it with our ETL process every so often. So the fact that a particular transaction that happened a minute ago is in or not in is less important. It's all about that bulk import. And partition tolerance is unimportant because the data really doesn't change. So we're less focused on those, and we're really, really focused on availability. So because we're optimizing for availability, each of our horizontally scaled nodes has maybe a subset or maybe the whole data set, and that allows us to be able to get massive performance through our system, where otherwise we wouldn't be able to. So here in our data warehouse, maybe we have a really, really wide set of nodes. They're all similar or the same, and so we get much better performance. So these are some of the experiments that we started to do here in our data warehouse. Let's remove foreign keys. We don't need to validate those because we're not writing. We can optimize indexes for analytical processing because, well, we don't need the transactional indexes. Let's denormalize the data. Our goal with data normalization was to store it smaller and avoid redundant writes. Here in a read-only system, we don't have those concerns. We can spread out a little bit and optimize for reads. We'll experiment with other storage mechanisms, maybe a column store, maybe a NoSQL store, maybe other stores to be able to optimize for that read experience. And we can horizontal scale to get more copies of our data so that we're not blocked by network I/O or disk performance. We got our data warehouse to be very different from our transactional system and really optimized for that analytical process. That is excellent. Denormalization makes analytics fast, and the schemas can evolve differently between the OLAP and the OLTP systems. Excellent. In our data warehouse, we have a separate read-optimized data store. Well, as is always the case, our needs start to evolve, and we can take a look at other concerns that we have here with our data. So how do I query across teams? Well, that was interesting. Each data warehouse was optimized for a particular team's content, and the transactional system and the analytical system were managed by that team. And now I want to do organizational wide queries, which means I need to query into everyone's data warehouse. Uh-oh. We had lots of little databases. We had lots of little data warehouses. And it's difficult to discover those data stores. Maybe they're hidden behind corporate silos or behind filters that don't really yield the results that we're looking for. And even if we do discover these other data warehouses, it's difficult for us to query across them. Okay, so our data warehouse, we really optimized for that query experience, but we optimized for it locally locally to each team. So now that we add cross-team organization-wide constraints, now it's difficult to discover each of those data warehouses and to be able to cross-collaborate them. Maybe we do discover each of those data warehouses, but now we have to match data. Is your customer ID the same as their customer ID? Or is there a different field? Am I just matching by name? Yeah, that's difficult. It's difficult to query across silos. So maybe we could ETL between data warehouses. Now, we got pretty good at this ETL process to get data out of our transactional system into our analytical system. So let's just, I don't know, explode the ETL again, move data from this warehouse to that data warehouse. Or we can upgrade to a data lake. Now, how's a data lake different from a data warehouse? In a data lake, we're consolidating all of the data warehouses into one large spot. Now, this data lake may not be exactly the same type of databases in all of these places. After all, we're pooling all of these different data warehouses together, but we have it organized to be managed by a single team that can really focus on availability and access and universal description. So, for example, here's each of our teams, and they have a transactional database. We have an ETL process that will make this data available, and we're going to pool all of our data warehouses together into this data lake. Now we can start to build a data catalog across all of these data warehouses. That's pretty cool. Now our analytical users can use the data catalog to know where in each of these data stores it needs to find the data. And ultimately, now we can get cross-team, organization-wide queries in this data lake. Let's unpack that a little bit. Our data lake. Now, here in the data lake, they aren't all the same type of database engine. They aren't all the same type of data. They're coming from different teams. So unique schemas are welcome, different storage engines, duplicated data. All of that is welcome here in the data lake. The goal is not to conform the data. The goal is to have a team of carefully chosen experts ensure the availability and discoverability of our data. So now we can query across all the data in the enterprise. Excellent. Now we can build really interesting things like data marts. Let's create a new view over the top of one or more data lake properties. We can start to create unique understandings of our data. Now, this doesn't create a new data warehouse, or maybe it does based on caching, but this new data mart can be able to create these data products that may not have existed before inside the silos. Now, each of these data products has a specific SLA, performance requirements, and other needs. So the data lake, it is managed by a team of experts. Now, these experts can ensure performance and availability. They can ensure the ETL jobs run successfully. Now, that's excellent. We now have a highly available data store. Kind of. So how do I get my team's data into the data lake? Yeah, that team of highly trained experts is now the limited resource. So now I start competing with other teams to try and get my data hosted in the data lake. I've got analytical customers who are wanting to be able to consume this data, and now we have to wait for the data lake team's backlog to get around to my data. We have contention between teams, and that team that is managing the data lake is less informed about the particular needs of my specific data store. They're more focused on availability. So what's in the data catalog? Well, it may describe the contents of my system, but if anyone pokes at it in any detail, the specialized team, the data lake management team, probably doesn't understand that data. They don't have that domain knowledge. And so, well, I don't know, go talk to them. Yeah, we end up with a big data lake that is starting to turn into a data swamp. The data swamp. We have highly available data. We have a nice data catalog across it, but the data may not have meaning. We have a data swamp. When our data starts to mildew and go bad. Our data lake. On the upside, that organization that focused on availability is able to create these data marts and this data catalog that allows us to be able to query organization wide. Excellent. On the downside, they're now the limited resource. So each team trying to get their content into the data lake hits contention with this uh, team of experts, and the team of experts are not domain experts on each team's data. They're experts on availability and performance. So usually it's a leaky abstraction, and as we're cruising through the data catalog, we need to now loop in various teams to say, can you explain this to me? Oops. Our data lake was really powerful in giving us availability, but it's really easy to turn that data lake into a data swamp where our data is available but meaningless. It's available and discoverable, but it doesn't necessarily make sense. Uh-oh. So a few years later, we're in this data lake experiment. We've gotten highly available data. We're able to query across our organization, but now we need to loop in others to be able to make sense of it. And we're still competing to try and get new teams' data into the data lake. And how do we avoid the data swamp? Yeah, the data swamp is really painful. So with the data lake, we consolidated to prioritize discovery and availability. And in the process of hitting discoverability and availability, we compromised on domain knowledge and data quality. Was it worth it? Maybe, maybe not. So let's take a look at data mesh. Data mesh is focused on solving that problem of data quality, hopefully without compromising data availability and performance. What is data mesh? It is a consolidated, centralized data catalog and separate analytical data stores. We're centralizing the data catalog, we're not centralizing the data. That's really cool. Let's take a look at our diagram here. We have lots of teams that are able to create their transactional systems. We have this ETL into their own data mesh node that is their data warehouse, their OLAP system, their data lake node even. And they're responsible for getting data into their data mesh node. We then have a data catalog that is able to index each of those data nodes, maybe even including our data lake. That data catalog allows our users to be able to discover data in whatever places that they are. And we can create these unique data products that may pull from one or more data warehouses, data mesh nodes, that allows us to yield unique insights. Now, each of these data products, like the data products that we created in the data lake, has an SLA, has performance guarantees, and ensures the quality of that data. Our data mesh is a collection of these data nodes where each data node is stored by the team that creates it. Now we don't have a contention around creating these data lake nodes. Each data mesh node is propped up whenever it's ready. So data mesh, it is a methodology, not a product. In data mesh, we have distributed data storage and a central data catalog. We present data as data products with an SLA giving us performance and availability guarantees associated with that data. It's distributed, meaning it's managed by the people who have domain knowledge over that data. Domain experts that maintain the transactional system now also maintain the analytics store too. That ensures that we have really high quality data, that we're creating a data catalog index that allows us to be able to discover that data in very meaningful ways, the people with domain knowledge are managing that analytical store. Data mesh. I like the analogy of a grocery store. If I'm in a grocery store and I'm in, let's say, the bread aisle, I'm looking through all of the different types of bread. I can compare the labels on their sides. I can pick the bread that I really like. Now, the grocery store didn't make any of the bread, or maybe very little of it. Instead, it organized all of the brands of data into one discoverable catalog and allowed me to compare them really easily. Now, this analogy breaks down a little bit because in data mesh, we're actually not hosting the bread inside the store. Rather, the store is just, well, an index. And so, yeah, we still have to go out to each bakery to get the bread itself. But we can see that analogy where inside the store, I can start to discover and compare data from different data sources and choose the one that best meets my needs. I can compare their labels. I can consume some of their data. I can do some experiments and see which data store works best. Each of those data products has an SLA that gets them into that data store and allows me to be able to compare and contrast and choose that one that best meets my needs. Data mesh. It's a methodology, not a product. On the upside, it's faster to enroll new data products. We don't need to wait for that highly specialized team. The domain experts that manage the transactional system also manage the analytical system. So we get higher data quality, we get better domain knowledge of that system, and we can produce results that are really meaningful and helpful. Ideally, we have that consistency and availability to rival the data lake. We build these as data products with SLAs around them. On the downside, we don't have a central control over that data storage. So maybe there is some cross-team collaboration that needs to happen to make these data stores highly available and performant. Maybe we end up with a little bit of duplication in that effort. Maybe the team of experts is now embedding themselves in the other teams, helping them to get their data mesh nodes online and enrolled in the data catalog. And then stepping back to let the team manage their systems. On the downside, it's also possible to lose track of some things. Maybe it didn't get into the data catalog and it's back to being a silo node out in the middle of nowhere and difficult to discover. Yeah, if ever we end up with a data mesh node that doesn't end up in the data catalog, how do we know it exists? Data mesh. It is not a technology, it's a methodology. So taking a step back, let's dig into data mesh and see if we really want to jump onto this, or do we want to just skip this one and wait for the next one? I like to compare data mesh and microservices. When we take a look at data mesh and microservices, we have lots of little pieces that are easily exchanged and interrelated. Each entry in our data mesh does one thing and does it very well. And we can combine these in interesting ways to produce new value that we didn't have before. Like microservices, with data mesh, the whole is greater than the sum of the parts. Our centralized data catalog and distributed data storage allows us to discover the data that we need and consume it based on the results of domain experts that could create this really high quality data in elegant ways. Data mesh and microservices are more than the sum of their parts. Next up, let's take a look at data mesh and DevOps. Now with DevOps, we moved from a developer team and an operations team kind of throwing things over the wall to a team where we could collaborate between these, a multifunction team that was able to do really interesting things. They focused on problems, they had unique skills to bring to this, and they were able to create really elegant solutions for deploying faster. Similarly, with data mesh, we can bring together the domain experts that manage the transactional system together with the performance and availability experts to be able to create these data mesh nodes, enroll them in the data catalog, and make them highly available data products with SLA guarantees in the same way that we had SLA guarantees with our data lake. That same team that was responsible for the transactional system is now responsible for the analytical system, empowering them to prop up the node whenever they need to and ensure data quality without having to need to wait for that team of ninjas to come in and bless their system. So what about the data lake? I'm not done amortizing the cost of my data lake transition. Why should I jump on this data mesh thing? Well, the cool part with a data mesh is that each node can prop up when it's ready, and we'll organize this in our central data catalog. So our data lake becomes one of the nodes inside of our data mesh. It has data, it can be highly available, and until we can redistribute that data back to the teams that create it, then yeah, the data lake is one of the nodes in our data mesh. That's excellent. We can enroll it in our combined data catalog, and if that's the easiest way to get at this content, then it's still available to our organization. Excellent. So should I dump all my technology and start over? Data mesh is not a technology, it is a methodology. Now, there are tools that can help us to create data lakes, data meshes, but it's not a dump the data lake and start over type of methodology. The data lake becomes a node in our data mesh, and that mechanism that we used for data warehouses is still applicable here in our data mesh. Our goal is to create a central data catalog and distributed data owned by the teams who have domain knowledge of that data. So yeah, maybe we need to distribute our team of experts into the teams to be able to facilitate getting their data mesh nodes online. But we're not laying off tons of people. We're not abandoning our previous investments. So ultimately, should I skip this one and wait for the next one? I would argue no. Data mesh is not just the next step in the ladder. Like DevOps, like microservices, it is a methodology change of how we organize data throughout our organization. Central data catalog, distributed data owned by the domain experts, allows us to get organizational-wide insights without a ninja team that becomes the bottleneck. Is it a fad? Well, let's look at some other fads that turned out pretty well. The internet, agile, DevOps. These were all really revolutionary, really unusual concerns at the time, and each one has proven to be the new methodology for how these things are done. I would propose data mesh is that new methodology for how data storage is done going forward. Data mesh. The methodology of data mesh is we discover data across the organization. We easily publish new data products into the data catalog, and domain experts managing that analytical data can focus on data quality in ways that we couldn't with the data lake. Ultimately, is data mesh right for you? I don't know, but take another look. You can grab these slides right now at robrich.org, and if you're watching this video on demand, hit me up on Twitter at rob_rich. Let's continue the conversation. For those of us here live in the event, I'll join you in that spot where the conference is designated for a live Q&A, or yeah, send me a tweet. It's been a lot of fun getting to join you here on Cloud Native Data Management Day. I'm so glad I was able to share with you data mesh, and I hope this is valuable. Thanks for joining us.